summed up into literally.
Hey, we're recording now. We can't, the internet will know we're having a lot of fun. It sounds like this class is having a lot of fun right now. We need to stop that. Just we're very serious in this class.
And you're confirming.
Yes.
You can block all this.
Flannel Friday. Good to see someone else in the crowd wearing flannel on Flannel Friday.
I didn't know that's what it was.
You're
I'm close.
close. Yeah, he's Flannel Junior on that shirt, I would say. It's not quite there. I did flannel Wednesday and Friday this week. And Thursday, too. I did half the week was flannel. Because, have you looked outside? Nobody wants to get dressed up when it's pouring down rain.
Quite honestly, why do you dress up? I mean, having a necktie.
I feel good.
In
I
comparison,
look good. I feel good. It's great. Yeah.
In comparison, having flannel is more comfortable, and you think that you look like you are formally dressed almost.
Yeah.
I feel like you can go to sleep in flannel.
You can. Flannel's great. Flannel's the only negative thing about a flannel is it can get kind of hot.
Yeah.
That's the only thing.
So then you can unbutton them.
That is true. Okay. We, you may recall that we were lecturing on mechanical translational elements. And we were like, hey, they're cool. We should do them more. So we are. So we did springs first, right? And we were all, springs are just things that exert forces depending on how much you compress them or stretch them. Yeah? And that was fun. We had a good time. And then now we're going to talk about point masses. Okay? So a non-relativistic, it's a little pretentious to say non-relativistic because of course it's non-relativistic, right? But yeah, I mean, we're to be technical. Traditional point mass elements with mass m, velocity v, relative to an inertial reference frame, the velocity always is, and momentum p has the constitutive equation that the momentum is equal to the mass times the velocity. So, we're pretty familiar with that equation, I think, everybody, which is good. I opened the ones where it's already filled in, so you guys get to see this. But don't forget to fill this in. So once again, time differentiating the constitutive equation gives us the elemental equation. So, time rate of change of the velocity, we just leave it as is because we want to write our elemental equation in terms of our power flow variables, right? Which are, what's one?
Which one?
What's one of our power flow variables? But for a translational mechanical system.
Oh, force and velocity.
Velocity is one, and force.
Acceleration.
Force. Not acceleration, but velocity. Well, acceleration is related to velocity, but we take velocity and force as our power flow variables. Because recall that the power in a translational mechanical system is just equal to the product of the force and the velocity. So that's why. And then on the other side of the equation, so we have this dv dt, and the m is constant. dp dt is just the definition of force. So that's why we ended up with this force on the other side. So now we have a relationship between the velocity and the force, which is just Newton's second law, but rearranged. F equals ma, right? But dv dt we don't write as a. Okay, so let's look at the schematic here. The point mass has a position coordinate or a position derivative velocity one that describes its motion, but it's always referenced to an inertial reference frame, right? So it has to be some either constant velocity or zero velocity, which is also constant velocity reference. So that's what this depicts. And F is a force acting on the mass. That's pretty much everything that you guys have seen, right? Forces on masses, that kind of stuff. Okay. Point masses can store energy, making them energy storage elements, in gravitational potential energy, or, as will be much more useful in our analyses, in kinetic energy. So when they're moving at some non-zero velocity, they have kinetic energy, right? So 1/2 mv squared is that kinetic energy. And that's mostly what we're going to be considering, is this nice kinetic energy storage that it has. Great. So that's point masses. There's not a lot to them. Springs were a little more interesting, complicated. But let's think about, a point mass. We already talked a little bit about this, but what type of thing is that going to represent for us, a point mass? Sorry? Yeah, so it could be an object that we're projecting. It could be just some, maybe some object, like for instance, we'll often use the quarter car model as a common system to consider. But if you had a mass, that was almost a perfect square.
It was so close.
I know. I got nervous and messed the last one up on purpose, I think, because I was like, it's too much pressure. Okay, so we might model a car to be a mass, and it might have some other elements. Let's say like just a spring for now, a spring, and then it might be experiencing some like rough road or something, right? So we might have like some velocity input here. So we could model the whole, mass of the car as being, a point mass that just experiences these forces from the road coming through the suspension system. So really any object with significant mass. And by significant mass, we mean a mass that's significant relative to other masses in our system. Okay. Point masses can store energy. We already talked about that. Okay, so that's point masses. Any questions on point masses? Okay. Dampers. These ones are more interesting in terms of newness to us. I took a survey in the first class. 0 people had seen dampers before in a class. Is that true now? Has anybody seen a damper? Okay, there's a few in this class that have seen dampers in analysis, which is cool.
Like in mass damper in building?
Yeah.
Okay.
Yeah.
I don't believe your first class.
First class, maybe they were just all asleep. It's possible. I am not exciting enough at 9 a.m., I think. Because I haven't gotten to the end of my coffee by that time. So, dampers are defined as elements for which the force through the element is a monotonic function of the velocity across it. Okay? So that's, a spring is an element for which the force is a monotonic function of the displacement across it. The damper is the same but for velocity. Okay? Linear dampers have the constitutive equation, and it turns out elemental equation. Force is equal to some damping coefficient B times the velocity across it. So it's already the elemental equation because the force and the velocity are already related. So you don't have to do anything to it. Now, we often call this viscous damping because systems that push viscous fluid through small orifices or those that have lubricated sliding are well approximated by this equation. For this reason, we typically schematically depict it as a dashpot, which is this figure 1.5. And I'm going to, we probably haven't seen dashpots before, or many of us haven't, so I'll draw it as an exaggerated like a piston cylinder sort of setup here, where we have a cylinder with fluid in it, and we've got a piston. Hmm?
Like a hydraulic piston?
Like a hydraulic piston, exactly. And say we're like pushing this piston through the cylinder, and there's fluid in here. Okay, so this is closed, and there's a fluid in here, and there are holes in this piston, so that fluid can flow through the piston, but it resists it. I mean, they're just like they're not tiny holes, but they're small enough holes so that fluid can go through, but they can't all rush through at once, right? So when you do this, it turns out that the force you have to apply to move that piston is proportional to the velocity that you're pushing it through. So the faster you go, the faster you go, the more it resists, okay? And you might think, like, I'm not super familiar with these mechanisms, but you are, actually. The doors, so even this door here, now you'll never be able to walk through a door again without seeing these. So that little weird thing up on the door, that is essentially a damper or a dashpot. They have different geometries, but the idea is that you have to force fluid through an orifice, and it makes it resist moving fast. So the idea is you can't open a door fast or close a door fast. You can move it slowly, and it doesn't really resist you, because notice when the velocity is small, the force is small. So, but when the velocity gets faster and faster, it resists more and more. So it's perfect for a door, which you don't want somebody to be able to just slam open or slam shut, right? So if you open, you could hit somebody. Shut, you could pinch fingers, or you could, make a loud noise. So.
Is it like similar to the seat belt?
That's a good question. I think that's a different mechanism, because the seatbelt, it locks in when you pull fast, right? But it is, if you pull it out slowly, but if you jerk, it locks. But it doesn't, I don't think it's a damper, although it would be kind of interesting to design a seatbelt just as a damper, because that's really, it doesn't really need to lock. All it really needs to do is stop you when you want to go fast, right?
I think that would be a lot safer.
Yeah, I actually have never even considered that, but there you go. This is a good idea.
Seniors on project.
Should do it for a damper seatbelt. Just like fill the car with fluid. No problem. So I learned about this damper thing on doors very first hand when I was pretty young, because I took a running start at a door that had one on it. And surprisingly, I won and not the door, and it just went pop. And then this oil started just falling out of the damper, and I was like, oh, I guess that's what's in those things. I didn't know that. So that was fun. But they're, so you should play with the doors after this. Just like if you go slow, it doesn't really resist that much. But then if you try to go fast, I'm not going to recommend the running start.
So do dampers, are they restricted to only like struts and stuff like that, or can they come with springs too?
So a damper, so there are the actual discrete elements like these that are like specifically made to be dampers and dashpots like this. And then there are also, there's using the damper as a model for something that doesn't look like a damper. So for instance, this is true for like the quarter car model as well. The suspension system doesn't necessarily have a dashpot in it, but it effectively behaves that way. It behaves because it damps out, right? If you had a spring and a mass connected and you just like let that system go, it would just oscillate forever, right? But clearly that doesn't happen in most systems. So we often will just say there's some damping in it, and we model it as a damping element. So yeah, it doesn't have to be like a specific discrete element. And actually, I'd say that it's rare to actually. It's relatively rare. We use the damper as a modeling element a lot more than we actually see a damper in a system. It's also used a lot for modeling lubricated sliding. So if you have two parts that are sliding and it's lubricated, the faster you go, the more it will resist. It will have like a friction force that's proportional to the velocity. It works for modeling bearings this way, for rotational ones. We'll get to that. But for linear sliding, if it's a lubricated surface, then it is reasonable approximation. Now, I would say this is the least easy to model this stuff. We use the linear damper a lot, but I would say that this is the easiest one to be nonlinear. The damping is often nonlinear, and so it's tough to know what to do. So a lot of times what we do is we have a pretty good prediction of the mass and the spring constants, and then we'll do some measurements to determine what the damping should be, what the damping model should be for a given system. You can come up with some approximations, but oftentimes it's tough to know. Linear damping is a reasonable approximation of lubricated sliding, but not a very good approximation of dry friction or Coulomb friction. So those types of friction, is sort of dry sliding, is not well approximated as being proportional to the force being proportional to the velocity. So in physics class, you guys looked at dry friction, like a block sliding. Like there's first off, there's the static, and then there's the dynamic coefficients of friction. That's a model that is for dry friction, and it works better than this does for dry friction. This isn't great for dry friction. So keep that in mind. I would say that in mechanical systems, in machine design stuff, often we lubricate any sliding that happens, so you can use this sort of a model to approximate that. Yeah, but dry sliding is pretty complex. I mean, you think about it, it's a really complex thing. It's a bunch of rough surfaces that are like mating and unmating and tearing and sliding across each other at this small level. So it's really like the fact that we can even approximate it with these simple models is a little surprising, but it's cool nonetheless. Aerodynamic drag is quite velocity dependent, but it's rather nonlinear. So drag isn't very well approximated by equation 112. It is better approximated by this expression, which is essentially quadratic, right? It's velocity squared, where c is the drag coefficient. Now, this is also an approximation, but it's better. But what does this say? I mean, this is really bad news if you want to go fast, right? Because like the faster you go, like it's the square of the velocity for aerodynamic drag that resists you. Mm-hmm. So that's why. Well, back in was it the 70s or 80s when they had the fuel crisis thing, and people were like lined up at gas stations trying to get gas.
I think that was in the 60s.
I think it was 70s, yeah.
You guys ever watch Miracle? That's why I remember it was in the 70s. You ever watch the hockey movie?
No, I've never seen it. Good? I usually like sports more than sports movies. Boxing movies, like, I hear that Creed is, like, really, really good.
Creed's alright.
But, like, I've seen so many boxing movies, and I'm like, I don't want to watch another boxing movie.
Same story.
Creed's alright.
No.
It's just what they did
What-
to Rocky.
Like, but then,
was
like, I keep
horrible.
hearing, like, Creed, no, it's, like, so good. Like, you really need to watch Creed. And I'm like, you guys, it's boxing. Again. I would rather watch a boxing match. Like, let's watch boxing. That's fine.
Yeah.
Yeah, so
Ollie's.
they lowered the speed limits a lot of places in response to that because you get better fuel efficiency when you don't have to deal with all this drag force because you're really fast. There's that. All right. Dampers dissipate energy from the system, typically to heat, making them energy dissipative elements. So springs and masses are energy storage elements, but a damper is an energy dissipative element. All right. And then finally we have these sources. So an ideal force source is an element that provides arbitrary energy to a system via an independent force, so independent of the system force, meaning that you just prescribe it and it applies it. And it may, this is not like a discrete element like a voltage source or a current source in an electronic system. You can buy one of those off the shelf, right? Like they sell them. They don't sell these. They don't sell force sources. But you can think of a force coming from outside of the system, on the system, as being a source to the system. So, for instance, if you wanted to model the force that was applied maybe like in a certain impact, you would maybe say, well, the force maybe has like this sort of spike to it that happens, and we could write a function for this spike during impact, and then we would have, like, so say it's an impacting some object, and we say that object has some mass to it, so we'll model it as a point mass, which sometimes we draw a box for it, mass, and then it has some force input, which we'll say this is Fs, so this is Fs, our input, and we might want to know what the velocity of the mass would be or something on the output. So that, and maybe this is impacting something that is has some maybe ability to compress. So you could maybe model it as like a spring in there, connected to ground, and then maybe also it doesn't spring back fully. Maybe it dissipates some energy, turning it into heat. So maybe we'll also put in a little damper in there too. And you've got yourself a nice little mechanical system to work with. So this force source in the mechanical translational system isn't like a discrete element that you get. You're using the force source to model some force coming in to the system. So this would be like our force source. So it's more interpretive in this. It's just like the mass and the damper, a little more interpretive. The electronic stuff, like when we talked about a capacitor, we talked about an inductor, those are like actual discrete elements you can buy. In mechanical systems, some of them are, like you can buy a spring, but things behave in a spring-like way. It's the same with electronics, but we very rarely will think about electricity flowing around that's not in a circuit, in like a really controlled environment. So we don't really think about like how to model like current running through a certain type of surface, or a certain type of material. Although that's not completely true. Even so, when you start talking about sensors a lot, you start thinking about how current and voltage are flowing around just any old material. Yeah.
Generally, when you think of a force being applied to like a car or a rocket, the force is being generated by something inside of the system, and it's, for example, like a rocket would be losing mass. This isn't a good example of that sort of force.
So yeah, so it's your system is going to be defined by the boundary that you draw around it. So you could, rocket's tough because it's losing mass.
Yeah.
But if you were to think about like for instance the car situation, so you've got like an engine and then it's providing power to the system from its fuel. You could think of the engine as being a source, even though it is like in a certain sense part of the car system. You could think of the energy that it's providing as coming from the fuel, which we're considering to be outside. So it's providing energy in the form of, when we're about to get to the rotational elements, but in the form of torque, for instance. So it might be, you could consider maybe an engine to be like a torque source, or possibly you have your engine set up so that it could act as an angular velocity source that you could specify what angular velocity it's going to be rotating at. In reality, a lot of these things are neither exactly a force source or exactly a velocity source. You can have velocity sources as well. In the quarter car model, if you had say you had a mass modeling like the car, the body of the car, and then if you had the suspension being modeled by a spring and a damper, because it dissipates energy, it doesn't just oscillate forever. You could think of this point right here as being like, where the wheel meets the road, right? And so it could have some input velocity profile, Vs, where that's like considered the source. So it could look like this, right? And the velocity could just be the motion of the wheel given the road input. And of course that's a really simplistic model, but it's an interesting model, and this tuned spring mass damper systems that you guys mentioned, that's the heart of what suspension systems are all about. You're not supposed to, like when you go over a bump on a road, you're not supposed to feel it too much, right? The idea is if you had a completely stiff suspension system, you would feel that whole bump, right? Bam. But it softens it. But if it's sort of too soft, then what happens is you'll bounce, right? You'll have this oscillation that happens. So you want it to respond, but you also don't want to oscillate. So having it tuned correctly is important. Also, you could put this in a skyscraper. They do that. So that's one of the things maybe you guys have seen. But they put these huge masses. Well, sometimes they're rotational, but let's just think about translation for a moment. Put a big mass up in the top of a building and connect it to the structure. These things sway around, these skyscrapers. They're very tall and they're flexible. So when, for instance, wind comes, they move around and people get sick in them. They have gotten sick in these buildings because they move around too much. It's not a very good feeling when you're moving around on top of a building. I don't know this, I've never experienced it, but I can't imagine it would be a good feeling. Sounds horrible. I would be like, get me out of this building. But so they do is they put these big masses on top of them, and they're tuned. Some of them are active, others of them can be just passive, so that the motion, like the mass might move around, but the building hopefully won't be moving around as much. So you can like take some of that energy and put it into the tuned mass spring damper system. It's pretty cool, and you can do a similar thing for like vibrations coming through structures and minimizing them. So like you can like connect you You can bolt a tuned spring mass damper system to a structure that's vibrating, and if you've properly tuned it, you can reduce the vibration in the structure by instead having the stuff in your tuned spring mass damper system absorb that energy. It's pretty cool. I will do some problems on that.
I have a question. So in the earthquake,
Mm-hmm.
so some buildings will affect, some buildings will not affect. The vibration will not affect some buildings.
Mm-hmm.
Is that right?
Don't they?
Yeah.
They still get vibrated, right? They just the dampers stop them from swinging faster.
Yeah, earthquakes. I don't know as much about how they do that with buildings, how they mitigate that in buildings. I don't know if there are tuned spring mass damper systems specifically designed for earthquakes. That could be. It would be a good thing to try doing. I think, as I recall, I think with earthquakes, they what happens a lot of times is that they'll get like side slip that happens where like the structure will kind of come off the foundation, and then that's when things go really wrong. But yeah, I don't have a great understanding of how they do that for earthquakes for buildings, and I know that they make certain buildings so that they're like more able to withstand earthquakes, and others not as much. So I know in our region, for a long time, we didn't know that we were in an earthquake zone and just getting lucky for a long time. And so we made buildings that weren't made to withstand.
Yeah, I heard that if the earthquake is like the degree is low, will affect in some buildings, and if it's high, that the same building that I don't know how to explain it, but if it's
Yeah.
low the degree.
I see what you mean. Yeah. So it's not necessarily like a linear process where like as you increase it, like the same building will be affected more and more. It might be affected less with a more intense earthquake or more. Yeah, that could be true. It's interesting. I would like to learn more about it. I just haven't. But yeah, it's cool. Okay, so I got to move on, unfortunately, because I don't want us to get behind, because you guys wouldn't want to be like the behind class.